you go to your C+ software, you just open the 2022 version, which is the first implementation that contains the first implementation of the RRI calculation. And then you just create a new project. Okay, let's give the name project. And you go to data, because it's a data, it's computed in the database. You create an object here under miscellaneous that will be called, I will increase the window here, which under the tag name sigma from femdata. And here I will just create a new one, new OP2. So I have to set up the format because I can also import in a PCH file, text file. Of course, the unit should be translated here correctly because I'm always working personally in S unit and just clicking on the OP2 file that has been generated. And then you have to set some few characteristics. So R is a fluid, obviously, here. But you can use something else. There is two boundary conditions, two structural handling, so plate and shell. What it means, when it is plate, the pressure is always twice on the surface of the specimen. So you don't need to make some calculation of projected pressure. When it's shell, obviously the pressure level of the reflection wave depend on the angle of the normal to the incident wave direction, and then we have a lot of computation that added to the calculation. So when it's not a shell, use plate, it's faster. Boundary condition, it's acoustic boundary condition. There's only two. Baffle, that means your plate is on a plane and on a square rectangle aperture, and all around it's a rigid wall. So the two faces of the plate cannot really interact. One is loaded and the other is radiating. When you are in free condition, that means your plate is suspended in the air, so the two faces of the plate can see the acoustics. So there is interaction between the two faces. They are taken into account through some simplified diffraction correction. After you have a structure length, which is not the exact length, it's just a characteristic length when you have a cube structure, solid structure, spherical, or I don't know, some kind of 3D volume. In that case, below some frequency, we need to enter also diffraction condition, and this diffraction is computed from the wavelengths defined, spatial wavelength defined by the characteristic structure size length. The critical frequency can be set manually here, or when you are in when you have no wave number. Generally, it's better to put the wave number when you are in free condition. This wave number is a structural wave number of the shell you are working with. If you have no idea, you can, in place of delivering an OP2, select a few reference nodes on the plate and then make a virtual SCA model and use the virtual SCA number here to perform. It just is used in a free boundary condition. And then for baffled, you don't need this. After, you have to set the incident angle on the plate itself. Here we use symmetry. So the angle theta is between the wave incidence, wave direction, and the normal to plate. So z-axis in that case. And the phi angle is the angle in the plane of the plate with the x-axis. So here we have to use waves of which angle are distributed between 0 and 90 degrees, and with phi angle oriented also between 0 and 90 degrees. So we use 30 theta incidence and 20 phi incidence in that case. Total 600 calculations. per frequency to get this tabulation, or the calculation internally is done in 1/6 of octave. So I start the calculation. And see, this is some listing, in fact. So I have in that case about 10,000 nodes and elements. And the surface is just 0.2 multiplied by 5.3. And I see that the finite content is 69 modes, of which frequency spans from 175 Hertz to 7,916 Hertz. For the calculation, 38 seconds for this model, and then I return it. Add some comment if I like, and then the object is here, and by double-clicking here, we will perform additional computation we will see in the next presentation. And I stop this session here.